Hello everyone, sorry I couldn't be here today, but I will give you the notes for the last part of 15.2 through this video. Okay, so let's pick up where we left off yesterday. I just wanted to, or not yesterday, sorry, on Friday. And one more example before we started talking about some other things. So let's say we wanted to find the line integral of x ds where the path C is represented by this path, where we go from 0, 0 to 1, 1. So we go along the line y equals x to get to the point 1, 1, but then on the way back we go along the line y equals x squared. Okay? The idea behind this example is that there's actually two ways that you can do this. Well, probably the easiest way, not two ways that you can do this. The one way to do this would be to separate this into two parts. So we'll call this first part C1 and then the part on the return C2. So what we'll do is set up two line integrals. We'll say along C1, we'll do that one first. So first we want to parameterize the path y equals x. Well, if y equals x, then we can simply let x equal t and y equal t. And t would just be from 0 to 1 here. Okay, so then our line integral becomes the integral from 0 to 1. Now we're going to replace everything in terms of our new parameter t. So then we have t. And now ds, remember that needs to be the magnitude of r prime of t dt. So let's figure that out. R prime, if r, in case you didn't make that connection, is t comma t, since x is t and y is t, then r prime is just going to be 1, 1 for the vector. So then the magnitude of r prime is just going to be the square root of 2. Okay, so what we're going to integrate is actually t root 2 dt. And if you go ahead and integrate that, that's going to be root 2 over 2 t squared evaluated from t equals 0 to t equals 1, and we just get root 2 over 2. Okay, so the value of the line integral from the origin to 1, 1 is root 2 over 2. And now if we go along C2, okay, so now we have y equals x squared as the path on the way back. So I'm going to say let's let x equal t and y equal t squared. Okay, but since we're starting at the point 1, 1, what we could do is shift this over a little bit. So we're going to say, instead of starting at 0, 0, because that's what this means, let's put 1, 1. But since we're going to switch the direction and go backwards, we can do 1 minus t, and then 1 minus t would get replaced here as well. Okay, so the negative just indicates that we're going to go back. 1, 1 means, or this 1 minus t represents the fact that we're starting over here. This is just to preserve the direction, and you can kind of see here that if we're between 0 and 1 for t, you plug in 0 for x, or for t, you get the point x is 1, the point y is 1, but now when you plug in 1, you see that the x and y coordinates are both 0. So we're going from here back to the origin. Okay, so this is the parameterization. We'll go ahead and integrate then from 0 to 1. We're going to do 1 minus t. So we're doing x, which is 1 minus t in this case. So since we're at 1, 1, we're starting here. X is 1 minus t. ds, we're going to have to find that. So let's take a look at r prime. R prime of t is going to be -1. And now here it's going to be 2, well actually it'll be -2 times 1 minus t. Alright, so now if I go ahead and find the magnitude, the magnitude would be the square root of 1 plus 4 times the quantity 1 minus t squared. Okay, so that's going to be plugged in here. 1 plus 4 times 1 minus t squared dt. So all I'm doing is using magnitude of r prime dt in the formula here, and now we're going to integrate this. So it's kind of a tricky integral, but this 1 minus t is actually part of this square root, so we can think of what's inside of the square root as u. And anyway, it'll be 1 plus 4 times 1 minus t squared. Instead of to the 1/2 power, this goes up to the 3/2 power. We're going to need 2/3 out in front of that to cancel out this new exponent. And let's see, to undo the chain rule in here, we're going to need a -1/8. Okay, so if you plug in the bounds, you're going to get -1/12. That's what this fraction is. 1 plugged in here gives you just 1 to the 3/2. Minus, plug in 0. This actually becomes -1/12 times 5 to the 3/2. So this is the same thing as, let me take out a positive 1/12. Then I'll switch the order here. This will be 5 to the 3/2 minus 1. Okay, so now, final answer. The line integral of x ds, in this case, will be the two values added together. So we have √2 over 2 plus 1/12 times 5 to the 3/2 minus 1. Okay, so that's the answer to this example. We just add the two values together. Now, interestingly enough, I did want to show you how to keep or preserve the direction. It actually, in this particular example, wouldn't have mattered if we just kept it as t squared and then even went backwards here. Or we kept the integral and we just went from, let's say, not 0 to 1, but from 1 to 0. That would also work, and we get the same answer. And the reason is because we have an arc length parameterization. Okay, so right now, as long as we have arc length parameterizations for these, the order is okay. It's interchangeable, but it will make a difference later on. Okay, so important to keep track of that. All right. All right. So the last part, or the last half of 15.2, focuses on line integrals of vector fields. So let's start there. Line integrals of vector fields. Okay, so the idea here is that we're going to be given a function r of t, a vector valued function, which is going to have components x of t, y of t. We're going to interpret dr, so the derivative of the r function, to just kind of be dx and dy. So that's going to be our interpretation. For an oriented curve, we'll call C in 2 space, and vector field f of xy equal to little f of xy, little g of xy. Here's what we've been talking about. So the line integral of a vector field will look like this. We have line integral along C of f dot dr, and the way we'll evaluate these well, there's a few ways to do it. We can take the literal interpretation, which is we plug in little f of xy, g of xy, and we take the dot product of that with dx comma dy, and then this is the same exact thing as f of xy dx plus g of xy dy. And the idea is similar in 3 space. Okay, now we'll talk more about how to evaluate this when it's in terms of x and y. We're going to go ahead and go straight to what we've been dealing with, which is when we have a parameterization. So let's have this definition. Let's say f is a continuous vector field and C is a smooth oriented curve then the line integral of f along C is the same integral we've been talking about, f dot dr. And what we're going to do is parameterize that path like we've been talking about, and we'll just plug in that parameterization into the vector field. And dr will just be r prime dt. So that doesn't really change. Okay, so here's a quick example. I'll get to the meaning of what these are and all that stuff in a little bit. I know some of you are probably wondering. Okay, so let's say we want to figure out, switch colors here. The line integral of f dot dr, or the line integral of f along a path C, which I'll specify in a sec. Let's say the vector field has components cosine x, sine x, and C sorry about that. C is the path r of t represented by ti plus t squared j with -1 less than or equal to t less than or equal to 2. Okay. Alright, so pretty straightforward if we have all this given to us. In this scenario, we set up our line integral of f dot dr, evaluate it from -1 to 2, and f, which is cosine x, I'm going to replace, again, hopefully you're good at this, but at this point you should know from the definition of r that x is t and y is t squared. Okay? And so instead of doing cosine x, sine x, I'm going to do cosine t, sine t. I'm just plugging in the parameterization into the vector field. And now I'm going to dot that with r prime. In this case, r prime is just 1 for the x component and then 2t for the y component. So now we just evaluate the dot product. So this is the integral from -1 to 2 of cosine t plus 2t sine t dt. Integral of cosine is sine. And now we reach a point where we have 2t sine t. We really haven't seen this in this course yet, but this is a time where you could do integration by parts, and you can certainly feel free to do that. What was that formula? Integral of u dv is the integral, equals uv minus the integral of v du. You can certainly use that formula, or there's a nice little shortcut. I'm sure Mr. Pierce taught it over at BG. Wheeling students, you may not have seen this, however, it's very nice and convenient, and I recommend you learn it really quickly. Here's how I remember it. Okay, so instead of doing integration by parts, if you have the product of two functions, one of which is differentiable, and you can differentiate until, well, as many times as you need to until it goes to 0, then you can certainly do this. So for instance, 2t is going to be the function I'm going to differentiate. So that's what I start with. I take the derivative once, I get 2. I take the derivative again, I get 0. Now the other function, which is sine t, by the way, this is called tabular. I don't think I mentioned that. You take sine t and you integrate. So if you integrate sine t, you get negative cosine t. And now if you integrate cosine, or if you integrate negative cosine, you're going to get minus sine t. Okay, and you stop when you reach the line or the row that has 0 in it. And the way this works, you take this product and you add, you take this product and you subtract, and if there were more, you just keep alternating, plus minus, plus minus. Okay, so then here, product is going to be minus 2t cosine t, that's for this first one, and then now we're going to take this product, which is positive 2 sine t. Okay, so sine t minus 2t cosine t plus 2 sine t is the value of that integral from -1 to positive 2. So when we plug that in, looks like there's actually 3 sine 2's minus 4 cosine 2. And then we're going to subtract, if I plug in -1, so that's 3 sine of -1 plus 2 cosine of -1. This is the same as 3 sine 2 plus, using the opposite angle identity here, a negative angle with sine, you can pull a negative out, make this positive. So it'll be plus 3 sine 1 minus 4 cosine 2 minus 2 cosine 1. Opposite angle identity for cosine tells us that the cosine of a negative angle is the same as cosine of the positive angle. So this is probably the answer that you would have in the back of the book. And this comes out to approximately 5.84. Okay? So now, let's move on to more of an interpretation now, okay? So let's say we have a specific parameterization. So let's say if t is actually an arc length parameter, in other words, t equals s, then the unit tangent vector is actually equal to r prime of s. This is one of those properties from chapter 12, and this is because the magnitude of r prime of s is constant. We get 1 there for an arc length parameterization. Okay, so what we're going to do is look at the line integral formula and just kind of interpret what another way to look at a line integral along a curve in a vector field. Okay, so using this, I can take the line integral and evaluate from a to b. And now instead of plugging in r of t, we'll plug in r of s if that's the parameterization we have. And then we have r prime of s ds, which is just integral from a to b. And again, let me just group this as f dot t ds, since r prime of s is the same as the unit tangent vector. This is just another interpretation for the line integral f dot dr. But this is kind of nice because it really does break up the line integral in terms of its tangential components. So what I mean is this. Okay, so let's say we have a path C that looks something like this, and here's where we are evaluating a line integral. And let's say that at this point the vector field has a vector corresponding to this red vector. And now here's the tangential unit tangent vector. Okay, so this is one option. In this case, we say that the line integral of f dot dr, using the interpretation that we have f dot t ds, the dot product, if these angles here are, if the angle between these two vectors is acute, is positive. Okay, so hopefully you guys remember that if you take the dot product of two vectors and their angle is acute, it's a positive value. If the two vectors are perpendicular, then the dot product is, yes, hopefully you all said 0. And if the angle is obtuse, then the dot product is negative, which gives us a negative integral. So here are the three options. That's option 1, option 2. Again, we have a path. Maybe it looks something like this. And here's our point, unit tangent vector at that point. And let's say the vector field is perpendicular to that unit tangent vector. Well, in this case, the integral of f dot dr, which again can be interpreted as f dot t ds, in this case, this is going to be 0. Okay? And the last case, sorry for all the different color switching here, would be if we have unit tangent vector, and now maybe the vector field, the force corresponding to that vector field is kind of going in the opposite direction. Well, then that means that the line integral of f dot dr is going to be less than 0. Okay? Alright, so just some different ways to interpret it. Now we're going to get to a big theme for us that's going to be relevant throughout the rest of the unit. Work. Let's talk about work as a line integral. Alright, so far we know that work is the dot product of f dot pq. This is the way we defined it in chapter 11. Now what we're going to do is generalize this definition for, let's say a particle is moving from P all the way along this curve in several partitions. Okay, and let's say that we have a vector field somewhere on this path, but what we're going to do is actually zoom in and focus locally. So again, kind of like what we did earlier with defining a line integral, let's define this point as p sub k minus 1 and this piece, or this point, as p sub k. And in here we have some force. Let's call it F sub k star. And the idea is that since we're only looking at, and literally what we're doing is zooming in and saying, well, even if we're looking at this small little section, that locally the force isn't going to vary too much. Okay, so the idea is that we're looking at this particular vector in one little partition of this path, but it's not going to vary too much as we go a little bit to the right or left. Okay? So now the idea is we're going to find the work performed by a variable force. This is a more general concept than what we've been doing. Acting on a particle that moves along a curved path. So, gravitational fields, electromagnetic fields, you could even have kind of like a river or anything where we have flow, basically. And there's different forces that are affecting the way a particle or an object would be flowing through that stream or through the vector field. Okay? So now the idea is this. The force at that point, well, let's break it up into little component functions like we've been doing. So we're going to do little f of xy, but we'll use x sub k star and y sub k star since we're at that particular point. And same with g. And now, so there's our force. Our direction of motion can be really closely approximated by a vector. We'll just go from P. So what I'm going to do is connect this point to this point. And again, we're looking at a very small partition here. So from this point to this point, we're going to say that that vector from P sub k minus 1 to P sub k is the direction of motion, and that from this point to this point, well, that's just going to be delta x sub k, in other words, change in x and change in y. Okay, so pretty straightforward. So where is this headed? Well, since we know that work is F dot PQ, what we're saying is that for this little section, this little partition, that the work done by this force as the particle moves from one point to the next can be approximated by whatever this vector field force is, which is F sub k star. And we take that with the vector from P to Q, which in this case is P sub k minus 1 to P sub k, which is equal to the dot product of little f of x sub k star, y sub k star, g sub k star, g of x sub k star, y sub k star, and times delta x sub k, delta y sub k. So we take the dot product of those two, and we get f of x sub k star, y sub k star, delta x sub k, plus g of x sub k star, y sub k star, delta y sub k. Which looks familiar, doesn't it? Now, if we take the limit, so take the limit as the number of these partitions increases to infinity, now we have the Riemann sum from k equals 1 to n Sorry about going off screen there. I know some of you are probably bothered by that. And I'm not here for you to yell at me, so again, I apologize. We take the Riemann sum of this formula. And you guys know that once we do a Riemann sum, then this is going to become an integral. In particular, this will become the integral, line integral of little f of xy dx plus a little g of xy dy, which, if you've forgotten, is one method or one definition for the line integral of f dot dr. Okay, so in other words, work. So here's our definition. So if we have some particle and we have some vector field, okay, and we want to go from one point to the next, then the work, we say that this is, again, the work done by the vector field on a particle as it moves from, let's say, P naught to P1 is a line integral. We'll call this path C of f dot dr. So there's your meaning. Okay, the line integral of a vector field actually represents the work done by the vector field in moving a particle from one point to the other. Okay, it's pretty neat. And we'll do a couple of examples, and then we'll be done. Okay, so for example, let's say we want to find the work done by the force field f of x, y, z equals negative 1/2 x, negative 1/2 y, and let's say 1/4 on a particle moving along the helix r of t equals cosine t, sine t, t. And let's say t is just from 0 to 3 pi. Okay? So, I'm not even going to draw this vector field, but we have some vector field. We start at the point 1, 0, 0, and we rotate around the cylinder, kind of creating this helix shape. And then we end back here at the point negative 1, 0, 3 pi. So if you plug in 3 pi, you get negative 1, you get 0, and then you get 3 pi for the z coordinate. Okay, so now to figure out that work, again, integral of f dot dr. We're going to go ahead and, since they give us a parameterization, we're going to plug it in. So we're going to go from 0 to 3 pi. F is cosine t. So that's going to be, oh no, sorry. F was negative 1/2 x, and since x is cosine t, this becomes minus half cosine t. The next component will be minus 1/2 sine t, and then 1/4 is good. Then we're going to take the dot product of that with negative sine t. So I'm just going to take the derivative of cosine. Derivative of sine is cosine. The derivative of t is 1 with respect to t, so dt. Simplify this dot product. Let's see. We get positive 1/2 cosine t sine t minus 1/2 cosine t sine t plus 1/4 dt. So actually the x and y components go away. We just get 1/4 dt, and that's going to be 1/4, sorry, force of habit, 1/4 times t evaluated from 0 to 3 pi. So 3 pi over 4 would be the work done. Okay. One little remark here before we write down the last part of the section. It's just some notational things. The line integral of the vector field along a path C can also be written if we switch the direction. If we put a little negative in front of C, that means that we're going backwards. And if that's the case, well then our line integral is just going to become the opposite value of what it was in the first place. So that just to keep that in mind, that if we reverse the path, then the line integral, the work is going to be the opposite, which makes sense. From here, going this way, if the vector field performs 3 pi over 4 units of work, then it's going to have to do negative 3 pi over 4 units of work to go back along that path. Okay, so the last thing now. I said we were going to come back to this, and here we are. It's line integrals with respect to x, y, and z. Okay, so if we have the line integral of f dot dr okay, we can think of this as f dot dr dt dt, which is kind of useful. Then we can think of this as, let's see, little f, little g, so that would be the vector field f, dotted with dr dt, which is x prime t y prime t dt, which, and this is what we were trying to get to, could also be evaluated as the line integral from, or I'm sorry, the integral from a to b of f of x y dx, so that's this times that, plus g of x y dy. This one times that one. Whoop. G times y prime. Okay? But the key here is, so we've already seen this, but the key here is that you only want one variable. Okay? So we got to pick either x or y. In this case, the order matters. Okay, so what I said earlier about if we had an arc length parameter, it doesn't matter which way you go, you get the same value. Here it absolutely matters. So we'll do an example here. Okay? And again, this is similar in 3 dimensions too, but we'll keep things simple. Let's say I have the line integral of y dx plus x squared dy, which, by the way, is the same thing as the line integral of f dot dr, where f is the vector field y comma x squared. Okay? So just keep in mind that even though it doesn't look like the line integral of a vector field, it is. Okay, if you kind of undo the dot product, this is what it looks like. Alright, so now to actually do this, we need a path. So let's say C is the path here from 1, 3 to 4, 0. But actually we're going from 4, 0 to 1, 3. So from 4, 0 to 1, 3. And let's say that the equation for that parabola is 4x minus x squared. Okay? So here's what I would do. I'm going to stick with x's. Since I know what y is, I'm going to just plug in 4x minus x squared, keep dx. Now I do plus x squared dy. Well, I just figure out what dy is. Okay, so if I do dy, dy would be 4 minus 2x dx. So I'm just going to put 4 minus 2x dx in there. And now my bounds of integration, these are x values, so this is going to seem weird, but the direction is important. Since we're starting at x equals 4, you need to keep 4 in here at the bottom, and then we're going to end where x is 1. So this is how we're going to set it up. So this is going to be the line integral from 4 to 1 of 4x plus 3x squared minus 2x cubed dx, which, to save the time, you guys can do that, I'm sure. You get 69 over 2. Okay. The other option would be to turn everything in terms of y, but you'd have a parabola and you have to do some other nasty stuff. So this is probably the easiest way to do it. Okay, so this completes 15.2. I should be back tomorrow. Tomorrow we'll go over any homework questions you got, and I'll hand out your discussion packets. All right, see you guys.